In this video, we're going to be using the arc length formula to find the exact length of the curve for two examples. In a different video, we will talk about how is it that the formulas are the way they are. Let's look at this first example. We want to find the exact length of the curve that you see here for x values between 2 and 3 inclusive and y values greater than or equal to 0. So since we are looking at y values that are greater than or equal to 0, we're looking at the top part of the graph. And then we're looking at x values between 2 and 3. So what we are doing is finding the exact length of the curve for positive y values and x values between 2 and 3. So we're looking at this part of the graph. And what we're trying to do is we're trying to find that length, or the length of the curve between 2 and 3 for x values. The formula you can see here, you can begin by finding the first derivative and plugging it in. So for us, what I like to do is I like to begin by solving for y and seeing where that takes us. So we're doing a little bit of algebra. We have 36y squared is equal to x squared minus 4 to the third power. If we solve for y, we have y squared is equal to x squared minus 4 to the third power over 36. So we have y is equal to plus or minus x squared minus 4 to the third power over 36 inside the radical. This makes sense, and that is y could be positive or negative, and you can see that in the curve. You have positive y values and you have negative y values. But for our example, we're only looking at y values that are greater than or equal to 0. So for our problem, we are looking at y equal to, I'm going to write down what we have in the form of x squared minus 4 to the 3 over 2 over 6. Because we're taking the square root of the numerator, and that's what we're writing here as 3 over 2, and the square root of the denominator. Let's go back to the formula. If we go back to the formula, notice we need to take the derivative of y with respect to x. You can see that up here in the formula. So let's do that. Let's find dy dx. And dy dx, we can write it down as 1/6 times 3 over 2 times x squared minus 4 to the 1/2 times the derivative of the inside, which is 2x. We can simplify that. We can say that 3 times 2 is 6, and 6 divided by 6 is 1. So we now have dy dx is equal to x times the square root of x squared minus 4 over 2. Remember, the arc length formula is the integral from a to b, and that was from 2 to 3, of the square root of 1 plus dy dx squared with respect to x. So let's find out what we get when we simplify the integrand here. So here we have x, the square root of x squared minus 4 over 2. We're getting this information and plugging it into the formula. So the length of the curve is equal to the integral from 2 to 3 we're going to have the square root of 1 plus x squared times x squared minus 4 over 4 dx. This is equal to the integral from 2 to 3 of the square root of 4 plus x to the 4th minus 4x squared all over 4 dx, which is equal to 1/2 because we are taking the square root of 4 in the denominator, which gives us 2 in the denominator, and then we have the integral from 2 to 3. Now, the x to the 4th minus 4x squared plus 4, that can factor into x squared minus 2 to the 2nd power. So we're going to have the square root of x squared minus 2 squared dx, which we know we can simplify as x squared minus 2 dx, which is equal to 1/2 times x cubed over 3 minus 2x, and we're going to evaluate from 2 to 3. So this is going to give us 1/2 times, we're going to have 27 over 3 minus 6 minus 8 over 3 minus 4. So however you decide to do the next couple of steps, you skip a little bit of steps here and there. But I'm just showing all of the work so that we can review some algebra and review some integration. So this is going to be equal to 1/2 times 9. 9 minus 6 is 3. 3 plus 4 is 7. So we have 7 minus 8 over 3, which is equal to 1/2 times 21 minus 8 over 3, giving us 13 over 6. So the exact length of the curve from 2 to 3 for the x values and positive y values is equal to 13 over 6.